Just a little meme here for everyone. Okay, so complex numbers. So complex numbers consist of a real and imaginary components. Hopefully everyone's actually had a look at complex numbers in year 11. Definitely I know it's part of the study design, so you would have covered it, but some schools, they don't cover it in a lot of detail, or they just like skim over it, which is probably not the best, because this is one of the most important topics in Special 3-4. But yeah, let's get started. So complex numbers consist of a real and imaginary component and can be expressed in the form z equals a plus bi. And where did we even get the imaginary component from? Well, it's from this. It's from I, which is equal to root -1. So it's numbers that don't really exist, but are made to exist. So that's why it's imaginary. Just some common equations that you need to know. I squared, I cubed, I4, I to the power 4, I to the power 5. I mean, obviously you can do some quick working out and work it out, but just knowing that at the top of your mind is really, really beneficial. And after I4, it just repeats itself. So it's pretty straightforward. If you are given like I36, you know that 4 is a factor of 36. So it's just going to be the same as I to the power 4. Okay, complex conjugate. So the complex conjugate is basically the conjugate of a complex number. And it is denoted by the symbol Z with a line on top. Like this. So, for example, the conjugate of x plus yi is x minus yi. So, whatever the imaginary component is, you just do the opposite sign. So, if it's x plus yi, then it's going to be x minus yi. If it's x minus yi, then it's going to be x plus yi. So, you get the gist of it. Some properties of the conjugate. So, if you multiply a complex number by its conjugate, basically what you get is the magnitude of the complex number squared, and I'll show you how to work out the magnitude a bit later on. Another thing about this sort of stuff is you're not just going to get simple questions like what is the conjugate of this complex number? Like that's too easy. That's probably year 11 stuff. The sort of questions that you're going to get are not even proof questions, more like and I'll show you some questions a bit later on, but this sort of property is really exploited in multiple choice questions, where I give you a bunch of questions and sort of like ask you which one will give you this, and they give you like some weird answers for the multiple choice. And this z times z conjugate is equal to the conjugate squared is something that not a lot of students really remember or really sort of focus on. So a lot of the questions they forget to answer. And also just knowing off the top of your head that this is equal to this makes solving this so much straightforward. And as much time as you can save on the exam is, you know, going to be so beneficial for you. Okay, so here we just have some basic questions, just sort of like some year 11 revision stuff, I would say. So just simplifying the following. So 2i brackets I plus 3. So just using basic algebra rules. So 2i becomes 2i squared plus 2i times 3, which is 6i. And I squared we know is -1. So it's just going to be 2 times -1, which is 2 plus 6i as our answer. 1 plus I over 2 plus I. So whenever you're asked to solve something like this where it has a complex number in the denominator, this is when you're going to be using the complex conjugate. So what you do is you multiply both the numerator and the denominator by the conjugate of the denominator. So 2 minus I minus I. And that is how you can further simplify this, because then we'll just have a multiplication on the top. And what do we say when we multiply z and its conjugate? We just get the magnitude squared. And the magnitude, we find it the exact same way as the magnitude of a vector. We just square root and square the I and j components. So 2 squared plus 1 squared. Not the I and j. The real and imaginary. What am I saying? So we just square the real and imaginary components, and then we square root it. And then, but remember, it was conjugate magnitude, the magnitude squared. So square root effectively just cancels out. So we're just left with the numerator. For this one, we just use the rainbows method. So 1 times 2, which is 2. 1 minus I, which is minus I. I times 2 is 2I. I times negative I is negative I squared. Negative I squared. What is I squared? I squared is negative 1. So it's negative 1 over 2 squared plus 1 squared. So 4 plus 1 is 5. I'm just going to do my work on the left-hand side. So 2 minus 2 plus 1. So minus 1 becomes plus 1. So we're left with 3 minus I plus 2I, just plus I over 5. And you're welcome to leave your answer like that, or you can expand it to make it 3 over 5 plus 1 over 5I. But yeah, that's basically it for the sort of questions, the basic questions that you're going to get for simplifying. Oh, sorry, I completely forgot there was one more, which is this one over here, using the double rainbows method that we just used. So 2 times 32 is 64, minus 2I plus 32I minus I squared. I squared is negative 1, so minus negative 1, which is just plus 1. Oh, there's no denominator. Okay. So, adding the real numbers, 64 plus 1, 65. And then the imaginary, so 32i minus 2i, which is plus 30i. So that is our answer there. Okay, here we have some solve the following questions using complex numbers. Okay, so just solve it how you would normally solve a quadratic to start off with. For the first one, just going to move negative 16 to the other side. So we're left with x squared is equal to negative 16. And then we need a square root. So x is equal to positive negative square root negative 16. Okay, so now we encounter a problem. And this is how complex numbers were invented. How are we going to now solve? Because root negative 16 does not exist. So how can it exist? Well, we need to use I. So what is I? So I is negative 1. So we can multiply by negative 16 times negative 1. Oh, sorry, not negative 1. Sorry, what am I doing? Times I. And what is I? Root negative 1. So therefore, it will just become positive root 16i, positive negative 4i. Yep, so that is our answer there, positive negative 4i. Okay, next one. Okay, so when you have something like this, I would probably recommend using the quadratic formula. So x is equal to negative b, which is negative 4, plus minus square root b squared minus 4a is 1, c is 5 over 2a, which is equal to negative 4 plus minus root 16 minus 20, which is negative 4 over 2. So we have negative root 4 in the brackets. That's just going to be negative 4 plus minus root negative 4. Negative 4. Oops. Using I, that will become positive negative 2i over 2. And further simplifying that, it will just be negative 2 plus minus I. So that is our answer there. So those are our two answers for this question. Now, let me know again if you have any questions. I'm just skimming through this because I do want to go through some more exam style questions at the end. Oops. Okay, so here is something that is also very important when it comes to Specialist Maths 3-4. In Specialist Maths 1-2, you might have went over this, but not in a lot of detail. In Specialist Maths 2, we actually use this Argand diagram to actually visualize what we're actually doing in terms of complex numbers. And I'll bring this diagram up many times during the lecture today, as I'm just going through the content. Okay, so how do we actually read the Argand diagrams? It's sort of very similar to the XY linear plane that we're used to. We have an x-axis and a y-axis, but in this case, the x-axis is actually the real axis, and the y-axis is the imaginary axis. So on the real axis, we plot the real values, and then on the imaginary axis, we plot the imaginary values. So here is a few examples already. So for example, negative 1 plus I. Negative 1 is the real component, so it will be over here. And then the imaginary component is I. So plus 1. So that's why we pop it here. Okay, so next, looking at the polar form. So this is something brand new for year 12. You would have... you probably wouldn't have covered this in year 11. So what is the polar form? So the polar form is a way of expressing complex numbers that is different to the Cartesian representation. So the Cartesian representation is what we're used to, so something plus I. So the real and imaginary components. This is polar form. Polar form is a bit different, and the way that it's actually useful is it actually uses the angle and the magnitude of the complex number. So you can sort of think of it as like a vector. Complex numbers are very similar to vectors. Actually, the thinking, I would say, is very similar to the way that you would think of vectors. But there are some minor, subtle differences. Okay, so how does the polar form work? Well, so like I said, the polar form has a r component and a theta component. And the way that it works is we have z equals x plus yi, and we write it in the form r equals cis x. And what is cis? Well, cis of theta is actually just this, cos theta plus I sine theta. It's a shortened version of writing, cos theta plus I sine theta. So rather than writing cos theta plus I sine theta every single time, because that's actually what the polar form is, we just simplify to cis theta. Just makes it easier for us. So this is what it will end up looking like. So r cis theta. Now, what is r? R is the magnitude of the complex number from the origin. And the way that we find that out is using this formula over here. R is equal to the square root of the real component squared plus the imaginary component squared. So very similar to what we have just done before for vectors, as well as what we did for on the last few slides, I think. Yeah. So that's the R component. That is how you find the R component. Now, how do you find the theta component? Theta is the hardest part. And the way that you find theta is actually the angle that the complex number makes with the real plane. And the way that I like to think of it is using triangles. So we have 2 plus 2i here as an example. So we will always have an x component and also y component. So if you've done methods, think of it sort of like circular functions on the unit circle. Sort of think of it like that. We're finding what the angle is. So this is the angle that we're trying to find. So what we basically should do is, there's a very simple formula actually. It's just the imaginary component over the real component. And we find the tan of that. But what this will actually do is that we'll actually find arg z. We want the argument of z. And I'll show you what the difference is. So arg z is just any angle. And when you do tan image over real, what you're going to find is, sorry, it's not tan, it's tan inverse image over real. That makes sense. You're just going to find the angle in the first quadrant. So when the imaginary and real numbers are both positive. But what about if it's over here? Will it still be 45 degrees? No, it won't, because now the angle that it makes is much greater. So what will we use instead? So then we will need to know what that angle will be in that particular quadrant. So, for example, if it was tan inverse -2 plus 2i, the angle, if we did tan inverse image over real, ignoring the negatives and positives in this complex number, we will still get pi over 4 or 45 degrees. And now it is up to us to determine which quadrant that is in. So what is the equivalent value of pi over 4 in the second quadrant? Well, it's 3 pi over 4, because it's just going to be pi minus pi over 4. And this comes back to the symmetry properties of circular functions. So that's why I remind you guys to have a look at the units 3 and 4 methods and units 1 and 2 methods and spec 1 and 2 content before coming into spec 3, 4, because that is really important in terms of getting, understanding the concepts and being able to effectively apply the maths. If it was here, we would still get 45 degrees, but now we would need to determine whether it's, in the first, second, or third quadrant. And that, if it was in third quadrant, then we have to, set an appropriate angle. However, there is a domain that we need to follow. So this angle over here, it has to be between negative pi and positive pi. Let me just rub this out. So really important, this angle over here has to be in the domain negative pi to positive pi. So it's starting from here, open circle, going all the way around to here. So if we had a complex number in this quadrant over here, instead of having it pi plus, whatever that is, we will have it as negative pi plus that. So really making sure that we always have our arguments in the correct domain. And we'll look at a few examples. Okay, so let's look at a few examples. So first we have convert to polar form. So how do we convert this? First we find the r. So what is the r? Remember, r is just square root 1 squared, so the real component squared plus the imaginary component squared, which is root 2. And then we need to find the theta. So remember, it was tan inverse imaginary over real. Imaginary is 1, real is 1. So what is tan inverse of 1? Pi over 4. That's the base angle. Now, which quadrant is 1 plus I in? It is still in the first quadrant, so that is actually our theta. So therefore, our value is root 2 cis pi and 4. So this is the polar form of 1 plus I. Okay, let's move on. What about 23i? What is that? Now, instead of using this formula, we can just sort of like visualize it. Where is 23i I going to be? Well, what's its magnitude then? Its magnitude, without even thinking, is just going to be 23. Because just 23 in the imaginary direction, up. Now, what about the angle though? So, thinking of the Argand diagram, its angle is going to be over here. This angle over here. What is that? 90 degrees. So what is tan inverse of, sorry, let me just quickly think about it. What is tan inverse of, what is 90 degrees? 9 degrees is just pi over 2. So it's just going to be 23 cis pi on 2. And finally, root 3, I'm going to change this one to actually root 3 minus 3i. Okay. First step, finding r, pretty straightforward. Just going to be square root 3 squared, which is 3, plus 3 squared, which is 9. That gives us root 12, which is 2 root 3. Finding tan inverse or theta. So tan inverse of imaginary, ignoring the negative signs when you're doing this, because you just find the base angle over root 3. Now what is that equal to? And that is just root 3. So what is tan inverse root 3? That is pi over 3. But is pi over 3 our theta? No, it is not, because root 3 minus 3i is actually, thinking about it, in the fourth quadrant. So what is the equivalent of pi over 3 in the fourth quadrant? That's just negative pi over 3. Using our symmetric properties. So therefore our answer is 2 root 3 cis negative pi on 3. So that is how we convert from Cartesian to polar form. Now going the other way around. Going the other way around, polar to Cartesian, all we need to do is write it in the full form that I showed you. So remember, the full form is actually not cis theta, it's actually 4 cos theta. So what is theta? Just sub it in. Plus I sine theta. Simplifying this will give you the Cartesian form. So 4, what is cos 2 pi? That is 1. But what about sine 2 pi? Sine 2 pi is 0. So plus 0i. So therefore our answer is just going to be 4. Okay, so now just looking at the next one, 8 says 25 pi on 3. What we can just do is, before we even do anything, let's just simplify 25 pi on 3. We know that the unit circle repeats itself every 2 pi units. So let's find the equivalent angle in our domain. And our domain was negative pi to positive pi, if you remember from the previous slide. So just returning it to the original domain, we can just subtract 25 pi over 3 by multiples of 2 pi. So how many would we need? What about, oops. So we need something over 3. So 6 pi over 3, 12 pi over 3. Just check. So just subtracting minus 24 pi over 3, which is just subtracting 8 pi, we'll get to the exact same spot, so it doesn't matter. we will just get pi over 3. So basically 25 pi over 3 is the same as pi over 3. So we can just write this as 8 cis pi over 3 as opposed to 8 cis 25 pi over 3. So now, further working on this, we can just simplify it by writing it like this. So 8 cos pi over 3 plus I sine pi over 3, which is equal to 8. What is cos pi over 3? That is root 3 on 2 plus I sine pi on 3. So sine pi on 3 is half, so plus half I. And further simplifying, we'll get 4 root 3 plus 4i. So that is our answer there for this question. Again, let me know if you have any other queries in the chat. Moving on, what is this? Complex operator. Okay, adding and subtracting the complex numbers. Very, very, very similar to, very, very similar to vectors. So if we technically think about this, if we're adding 2 plus I and 1 minus I, and if we shift 1 minus I, to over here, because remember vectors, doesn't matter where they start from, as long as they have the same direction and magnitude, they're the same vector. What do we get? We get 2 plus I plus 1 minus I. That's what we get, that complex number. So just trying to show you the familiarity here. But basically, when we're adding complex numbers, if they are in the Cartesian form, all we need to do is add the real components separately and add the imaginary components separately. But yeah, that's basically it for adding and subtracting complex numbers. Very simple to vectors. Very similar to vectors. Okay, next, multiplication and division. So, multiplication and division. So, some guidelines for multiplication and division is always try to do it in polar form if it's possible. If not, then obviously you'll have to use the Cartesian form, which is a bit messy and gets really ugly really quickly. Polar form is just so beautiful and it's really designed for multiplication and division. And there's 2 really simple formulas for multiplying and dividing. Basically what we do is if we're multiplying z times z2, so z is r1 cis theta r1, and z2 is r2 cis theta r2. All we need to do is multiply them. We multiply the magnitudes, and that becomes a new magnitude of the new complex number. And then we just add the angles. Really being careful when we're adding or subtracting angles is we're taking note of whether the angle is positive or negative to begin with. Similarly, when we're dividing, we need to divide the magnitudes, and that becomes the new magnitude, and subtract now the angles. So for multiply, divide to r, and add, subtract to theta. So that's a rule that I like to follow. Some other really common forms or polar forms of something. So if we're writing the conjugate of a complex number that's already in polar form, we just take the negative of the angle. For reciprocal, we reciprocate the magnitude and we negative the angle or the argument. Okay, here we have a quick question. Simplify, give answer in polar form. So if we want to simplify this, what we need to do is first of all multiply the magnitude. So 13 times 4 That will be 52. Next, what we need to do is we need to add the angles. So 5 pi over 2 plus pi over 6 will give us our new angle. So just adding those will get... And if you're not asked to leave your answer in a particular form, you can just leave it in whatever form is convenient for you. In this case, it will probably just be polar form, because we're doing it in polar form. Five pi over 2, that will be 16 pi on 6. Okay. It looks like we're done, but we're actually not done. What do we know? We know that our domain is negative pi to positive pi. So we need to get our answer to that form. So what we need to do is subtract 2 pi to get it to that domain. So 52 cis 8 pi and 3 minus 2 pi. So cis 2 pi and 3. That is our answer. 52 cis 2 pi and 3. And we just leave it like that. Okay. Next we have the de Moivre's theorem. Again, something new. You probably wouldn't have covered this in year 11. And why do we use de Moivre's theorem? So de Moivre's theorem is really useful when we're putting a complex number to a certain power. So we need the complex number to be in polar form in order to actually use the de Moivre's theorem. So basically what we do is, if we're trying to find what any complex number to the power of n is, all we need to do is we need to take the same power to the magnitude and then multiply that by the angle. So z to the power of n is equal to the magnitude to the power of n, cis, n theta. So n times by the angle. Another use of the de Moivre's theorem is finding roots. So let's just say we are given 4i, let's just say, and we're asked to find the cube root, or, the fourth root. I don't think that has a special root, or the square root or something like that. Square root's easy. We don't really need to use it for that. But anything beyond a square root, it becomes complicated. We can't really leave our answer as like this. We can't really leave our answer like that. We need to find the actual cube roots, and most of the time they actually exist. Just something to notice here is that when we are finding square roots, we will have 2 solutions. However, when we're finding cube roots, for normal numbers, usually we'll just have 1 solution. But for complex numbers, we'll have 3 solutions. For fourth roots, we'll have 4 solutions. For fifth roots, we'll have 5 solutions, and so on and so forth. And they will actually be equally spaced out on the Argand diagram, as you can see here. So that is a concept that will be applied when we use de Moivre's theorem to solve equations. A little bit of a complicated process, and we will go through a few examples. But basically, when you're trying to solve an equation or find the cube root or something like that, basically what we need to do is first of all write the formula. So let's say we're asked to find, the cube root of something. First step, write the formula. Z to the power of 3 is equal to r to the power of n cis n theta. Convert the complex number into polar form if it isn't already in the complex form. Then we let Rn equal the magnitude and n theta equal the argument, and make sure the argument is in the correct domain. And then this is basically the formula. So z, or the solutions, are equal to r to the power of 1 over n. So if it's we're finding cube roots, then it's 1 over 3. Fourth roots, 1 over 4, so on and so forth. Cis, theta plus 2k pi over n where k is 0, 1, 2, 3, 4, depending on how many you need to find. If you're just finding 3 solutions, then k will be 0, 1, 2, and you sub in each one to work out what it is. I'll actually show you an example because that just makes a lot more sense. So let's just say we have this question here. Find the fourth roots of z to the power of 4, 2 plus 2i. First step is to convert it into polar form. So 2 plus 2i, first finding the magnitude, that's just going to be 4 plus 4, just squaring them. That's going to be root 8, which is 2 root 2. Just leave it as 8 to the power of, just leave it as root 8 for now. We'll come back to it a bit later on. Next step, so we're finding z to the power of 4 is equal to, we haven't really found the angle. So the angle, remember, is tan inverse imaginary over real component, which is 1, which is tan inverse of 1. Oops. Which will be equal to pi over 4. So now we have our equation. So root 8 cis pi over 4. Okay, so now that we know our complex number in polar form, let's just write it down. So 8 to the power of half cis pi over 4. Next, we just apply de Moivre's theorem. So remember, we're trying to find what z is. Z is equal to half cis, and this entire thing to the power of 1 over 4. So then, remember how we applied de Moivre's theorem? So the magnitude, we put that to the power. So a to the power of half to the power of 1 over 4 cis, and we multiply it by the angle. So 1 over 4 times pi over 4. Just one thing that you need to remember is, remember how I said if we're finding the fourth root, there will be 4 solutions. So how do we account for all those 4 solutions? Well, we just add 2 pi, but that will find us a solution that's not in the domain. We need to account for the fact that it's within the same circle and it's equally spread out. So we actually add 2 pi divided by 4. If it was cube root, then it would be 2 pi over 3. Actually, I have to write k as well, because we don't know what k is, how many times we're adding it. Remember, k was 1, 2, 3, 4, whatever. So that is how we actually find the solutions. Now, all we need to do is simplify it. So it'll just be 8 to the power of 1 over 8 cis pi over 16 plus 2 pi over 4, which is pi over 2. Comma, k is all integers. So k can only be an integer. It's going to be 0, 1, 2. I'm just going to erase this so I can work out the rest over here. So now all we need to do is find the solution. So what does z equal when k is equal to 0? Well, z is equal to 8 to the power of 1 over 8 cis pi over 16. K is just 0, so we can just ignore that next part. What about when k is equal to 1? Well, z is equal to 8 to the power of 1 over 8 cis pi over 16 plus pi 2 on k. Now we need to add pi 2. So it's pretty straightforward now. Once you've found the first solution, you just need to add pi on 2, pi on 2, pi on 2. But remember, that's only when it's fourth root. When it's cube root, then you add 1 over 3, 1 over 3. Oh, sorry, pi over 3, pi over 3. And so on and so forth. So k equals 1. K equals 2 now. Z is equal to 8 to the power 1 over 8 cis pi over 16 plus, and now k is what is it? 2 now. So it's going to be pi. And finally, k equals 3. Z is equal to 8 to the power of 1 over 8 cis pi over 16 plus, just gonna, k is now 3, so plus 3 pi on 2. And then you simplify it, and then one last thing that you have to do is make sure it's in the correct domain. The angle is in the correct domain. If it's not, subtract or add 2 pi, whatever you need to do to make sure it's in the right argz domain. But yeah, that's basically how you solve complex numbers using, not complex numbers, how you solve complex equations using de Moivre's theorem. Okay, next let's have a look at complex relations. So what are complex relations? So complex relations are relations on the complex plane. Basically, it's sort of like, you know how for just normal numbers we have equations. So like x squared, y equals x, y equals cos x, y equals log x, stuff like that. For complex relations, same thing. We have equations again. But this time, it's called a locus because it's not just an equation, it's thought of as a set of points that satisfy a certain condition. So for example, if the condition is modulus z equals 2, we are looking at all numbers on the complex plane that have a magnitude of 2. And what this sort of pans out to be on the Argand diagram is a circle with a radius of 2 centered at 0. So that's how we sort of look at complex relations. We sort of look at it from a geometric point of view as opposed to an algebraic point of view. Now, what about if we had this? What does that imply? Well, again, it implies a circle with a radius of 2, but now we sort of have like a shift. And that shift is z minus 3. So from the center, we're moving 3 units to the right plus I, and we're moving 1 unit down. So that is now a circle centered at 3 minus I. Or if you're looking at it in terms of coordinates, 3, -1. That is now our complex number. A complex relation. So this is the circle over here. Okay, so we have different types of relations that you will deal with within Special Maths. The first is a circle, probably the easiest one and easiest one to identify. Z minus A, that's the common form. Z minus A equals R. Z is, you just ignore that. Negative A is what our center point is going to be. So if it's Z minus A, then A is going to be our center point. So if it was Z minus, 1 plus, if it was Z minus 1 minus I, which is Z minus 1 plus I, our center point is actually going to be 1 plus I. If it was Z plus 1 minus I, Z plus 1 minus I, what will that be? Well, that will be Z minus -1 plus I. So center point is -1 plus I. Make sure you return it to this original form if you're trying to work out how to draw it. Because whenever we return to the original form, we can immediately identify that A is going to be our center point. And then R is the radius. Next, we have rays. So rays are basically just straight lines that have a starting point. So if we have argument Z minus B equals theta, basically what that is we have, again, a starting point, which is going to be B. That's our starting point. And then we just draw, we just draw a line with that angle that's given. So if the angle was pi over 3, then we draw a line with that angle, pi over 3. And another thing to note for raised is that the starting point is always at the origin and it's always an open dot. Actually, it's not always at the origin. If we have a translation, then it can move. Because if B is like, 1 plus I, then it's going to be centered at 1 plus I. That's the starting point. But the starting point is always an open dot. That's the important part. Okay, and then we have lines. So these are a little bit more complicated. Never do anything related to lines algebraically unless you're told to. The way that we do it is, again, using geometry. So lines are also known as perpendicular bisectors because basically what it is we have two separate points. So we have the point A, and we have the point B. And what we're actually trying to find is the perpendicular bisector to the line that connects them. So this is what we're trying to find. So we're trying to find a line that is equidistant from those 2 points. And we call that equidistant because every point on this line is equally distant from A as it is to B. Okay, so this is how we do them. So we graph the 2 points given, so A and B. We use the midpoint and gradient formula between the points. And that will give us the... so first of all, we find the midpoint between these 2 points. So let's just say we had... Let me use an example. Z minus 1 minus I. And let's say we had Z minus 2 minus I. First of all, return to the original form. Z minus 1 plus I is equal to modulus Z minus 2 plus I. So now 2 plus I and 1 plus I are our original, are our 2 coordinates, so A and B. So plotting it, we will get the coordinates 2, 1 and 1, 1. Now first of all, we find the midpoint between these 2 points. So if you know it from methods, the midpoint is just it's just x1 plus x2 over 2, comma, y1 plus y2 over 2. That is just what the midpoint is. Let me see. Oh yeah, so and then we find the gradient. And the gradient, pretty straightforward, y2 minus y1 over x2 minus x1. Excuse me. That will find you, so the midpoint that we'll find is this midpoint over here. And the gradient that it will find you is this gradient over here. But we're not trying to find that line. We're trying to find this line over here. So what we need to do is we need to divide the gradient by -1. Because remember, gradient of 2 perpendicular lines, so the gradient of a parallel line and a perpendicular line is equal to -1. So to find the perpendicular gradient, we need to divide the gradient from -1. This gradient over here that we found between the points A and B. Once we've determined the gradient of the perpendicular line and the midpoint, we can use this formula over here, y minus y1 over x minus x1, to find the equation. So what is y minus y1? Y1 is the midpoint y coordinate and x1 is the midpoint x coordinate and m is the perpendicular gradient. And then once you find the line in Cartesian form, you can just sketch it. It makes it really easy. Otherwise, if you know how to do it using this, then that's all good as well, but that gets a bit complicated.